Okay. Hi everyone. So I'm super excited for today's speaker, Alp Sipahigil. So Alp graduated from Michelutens in 2017. Then he did a postdoc at Oscar Painter's group at Caltech, working on things like developing quantum transducers. Since 2021, he's been at Berkeley. He's the faculty in physics, joint appointment physics and EECS, electrical engineering, computer science, and he's also a faculty scientist at LBNL. His group works on developing quantum hardware for all sorts of applications that I guess we'll hear about today. Yeah, so round of applause, and we're excited to have you.
Between microphone. Okay, great. Hello, everyone. It's a great pleasure to be here. Thank you for the invitation. So I've been working across the bay for the last 3 years, and what I wanted to do today, since we're so close, and as you know, our students started exchanging and giving seminars. What I want to do today is to give you a sense of the types of activities we do. So I'll go into some depth on some of the projects, but mostly what I'll be doing is talk about various projects we have going on. So I already had some really nice discussions in the morning, and I'm looking forward to kind of the more in-depth discussions in the afternoon. So please feel free to interrupt me with questions, and I'll be happy to go into details as you wish. All right, so there's a theme. It's not just the kitchen sink today. There's a theme to this presentation, and so it's about how to utilize and engineer defects both for photonic and superconducting quantum circuits. Before I start kind of my presentation, I want to acknowledge the team that does this work. We started our group in 21. We now have 5 students and 5 postdocs. And I also want to thank all the funding agencies for supporting our work. So our group works on both integrated photonic and superconducting quantum hardware. And I'll kind of talk about both sides a little bit today. So this seminar series is already kind of living in the quantum space, so I don't need to give a very kind of general introduction. But what I want to highlight is that we still have a lot of work to do. So a figure of merit that, one of the figures of merit that the community uses for characterizing your computational power is the quantum volume, which is some combination of how many qubits you have and how good they are. So this is a plot I pulled from Dr. Gill's presentation. If you pick ion trap or tweezers, the numbers are a little bit different, but I think the overall conclusions are kind of general, especially when it comes to solid state hardware. There's a lot of open challenges at the device physics level that we need to address to reduce error rates in qubits. So when we're trying to do quantum computation, we use physical qubits, and then we do error correction to implement fault-tolerant algorithms. But a lot of the kind of hard limitations right now come from errors that are related to device physics, materials, or control of our quantum systems. And there's also challenges related to scaling. So that's not something my group works very much on, but that's another thing that we need to address. But overall, I think this is a full stack problem. Like classical computing, it involves physics, materials, devices, circuits, systems, architecture, algorithms, and that takes many fields to make that work. And somehow, in this quantum field, we're trying to make all of that work. So we need to also be equally interdisciplinary. So a lot of the work I'll talk about has, some physics, some electrical engineering, materials aspects to it. And I think that's what it takes to make real advances on quantum hardware. So what do we do? My group, concisely speaking, as we work on integrated quantum device physics. So this is, in some sense, the analog of, when people in electrical engineering, they study transistors to death and try to understand everything about them. So that's what my group does. So we think about how to reduce error rates, think about new ways of implementing qubits, readout, control, and interconnects. we also try to do these things in a way that could be, scalably manufactured using standard semiconductor manufacturing. I think it's, my personal feeling is that we're still not in the transistor era for quantum computers. I think, one of the goals that we also have is, to figure out what would be the best device, the qubit device platform to take this to the next level. There's a lot of kind of promising hardware, which some of which I'll highlight here. So in the solid state domain, the kind of front runners are superconducting qubits. They're by far the most popular quantum computing hardware. They're great because you can lithographically define them. It's actually the length scales are pretty forgiving, and you can implement fast, high fidelity logic. So the nonlinearities are very strong. But because these are macroscopic quantum objects, they typically have short coherence time. So that's one of the challenges. On the other end of the spectrum, there are systems like nuclear spins where you can store quantum information up to hours. So that's really, from the coherence perspective, they're really good, but they don't interact with each other. And finally, integrated photonics allows you to transmit light over long distances with little loss, but they don't interact with each other. And all of these different platforms, these properties come from somewhat fundamental trade-offs. So if you have a strongly interacting system, it is kind of likely that it's going to have short coherence and so on. So in my group, we think about hybrid device architectures for two purposes. I'll come to that in a little more detail in a bit. What I mean by hybrid quantum systems or devices is that these different hardware have different strengths and weaknesses, and one of the questions is whether you can use modules to do some specific tasks. For instance, you could use qubits for your processors and nuclear spins to store information for extended times, and use optical photons to communicate. So one of the kind of obvious questions is that each of these systems by themselves are well understood, but how can we engineer interactions between these different physical domains? So how can I take a quantum information from the optical domain to a nuclear spin or to a superconducting qubit? So we think a lot about these interconnect problems, how to transfer quantum information and how to engineer interactions between these different physical domains, mainly for two purposes. So the first point is more about the engineering flavored motivation. Okay, it'd be nice, if I had a memory module, I can plug that to my processor, and I have an optical I/O. So the first motivation is to engineer this toolbox for quantum hardware. That's something we think about. But in today's talk, I'll actually focus on another aspect of these interactions, which is the fact that you already have these interactions going on all the time, right? When you build a superconducting circuit, yes, you have your Cooper pairs, and you can describe them by a macroscopic wave function. You can do quantum optics with it, but in real life, there's dirt physics. There's a real world condensed matter phenomena that happens, and your quantum states, even if you don't want them to, will interact with defects or interfaces or other phenomena. So being able to understand and engineer these interactions, it's not just about engineering modular quantum systems, but it's also about making each of these components better as well. So if we can understand how these different components interact, we can also improve the individual parts. So in today's talk, I'll kind of focus on different combinations of these systems. So in the first part, I'll talk about our work on developing spin-photon interfaces in silicon. Silicon is a very mature platform for photonics, but it only has very weak classical nonlinearities. So one of the motivations here is to introduce quantum nonlinearities into silicon photonics. So that'll be the first part. And in the second part, I'll discuss how interactions of superconducting qubits with defects, unwanted interactions, limit coherence. And we'll actually apply the lessons we learned from part 1 to part 2. Okay, so the talk is kind of divided into two parts. The first part is photonics, it's integrated quantum photonics. So in this first part, defects are good. We like defects, okay? So they'll be our qubits. In the second part, I'll talk about superconducting circuit work. And here, defects are things that we do not like. Okay. All right. So let's get to it. So in our group, we're working on developing solid-state hardware for developing quantum ether nodes. I guess I will not give a broad introduction what quantum networks are, not network nodes are. I think in this community you have lots of projects, and you've heard about this quite a few times. So one of the key requirements here is develop modules where you can both store information, let's say in the spin state or hyperinfine states of atomic system, and entangle that with optical photons such that you can distribute entanglement. So there are already a variety of platforms. Systems like Color Center have the advantage that you can engineer them in compact solid-state devices. You can integrate them with optical fibers, but a lot of the work, a lot of pioneering work in this field happened with material platforms like diamond, which are kind of hard to manufacture. There's a lot of nice work going on, but I think it's still a challenge to do things like diamond photonics to the level that we want them to do. And secondly, the existing color centers are usually invisible. For technological reasons, we'd like to implement these light sources, quantum light sources, at the telecom band. And if you ask any engineer, what kind of hardware platform, material platform they want to make electronic or photonic circuits in, silicon is the default answer, because we know really well how to make very advanced electronic and photonic circuits in silicon. So in my group, we're studying, silicon is great for electronics and photonics. And for quantum applications, it's also well known that it is a very high quality crystal, and you can isotopically purify it, and you can have both electron and nuclear spin coherences that are really, really long. So this is a plot where I guess the T2 time was 40 minutes or so. So you can engineer the wafer to be very low noise in terms of the magnetic noise. So all of this is great, and there's a lot of nice work on spin qubits in silicon, but what has been missing is optically active defects in silicon. In the past few years, there's been kind of really encouraging breakthroughs. In particular, I have to acknowledge Stephanie Simmons' group at Simon Fraser University, where they've shown that this defect called the T-center kind of satisfies a fair number of these criteria. So let me kind of walk you through this defect. So we start with the silicon host. We create a defect which has 2 carbon atoms and an extra hydrogen. So compared with the color centers, this is a little bit complicated. Basically has 3 atoms that need to come together. It's a little harder to make them, but us and others have figured out recipes to reliably make these defects. So this is a system. It's a defect that has a spin 1/2 ground state, electron spin ground state, and it also has an optical transition in the O band at 1300 nanometers. It has 2 excited states that are split by about 2 MeV. The splitting of these excited states determines the operation temperature. So we need to operate them around 3 to 4 Kelvin. Okay, so your H bar omega needs to be much less than this 1.8. That's the gap we need to worry about. So the excited state lifetime of this defect is about 1 microsecond. So this is slower than quantum dots or like diamond color centers, but it's a lot faster than rare earths. So it sits somewhere in between. For those interested in the solid state side of these things, it's a defect-bound exciton, and the physics of this is quite different from deep defects in wide bandgap materials. So that's something also on the spectroscopy side we're studying. But for kind of the quantum community, what we often do, right? We simplify the systems into 2-level, 3-level. We start drawing these lambda systems and such that we can identify how to control and read it out. So if you apply a magnetic field, the ground state splits into 2 electronic spin states. And these defects also have nuclear spin, so you can use the hyperfine interaction to also control the nuclear spin states as well. And the Simmons and the Mike Tewell's group at SFU have measured good coherence times, both for the electron and nuclear spins in bulk isotopically purified silicon. Yeah.
Where does this change thing come from?
It's from the hydrogen. Yeah. You can, of course, choose carbon-13, but yeah, the default nuclear spin comes from the hydrogen. So we started creating these in our lab. We reproduce in spectroscopy similar values to what has been observed. So here I'm showing you the laser spectroscopy of an ensemble of T centers creating a silicon photonic waveguide. As you can see, we have an inhomogeneous broadening of about 0.2, 0.3 nanometers or so. Okay, so what I'm going to talk about today is kind of address, the challenge of realizing atom-like systems in silicon. So this has two parts: understanding the optical properties and also understanding the spin properties of these defects. So we're working on both of these. So in the first part, I'll talk about the platform that we developed, which we're using to kind of enhance the atom-photon interactions, also to play some fun games in the optical domain, which has not been done before. So let's get right to it. I think Lucas presented here a few weeks ago. So this is a platform that we developed where we want to embed individual T centers in photonic crystal cavities, such that we can Purcell enhance them. We can enhance the cooperative light matter interactions. One thing that was this is a new platform that we're exploring. So one of the things oftentimes in these experiments is that, you may not have the emitter in the cavity, so you might need to do the experiment many times. So early on, we were thinking that, okay, why not just make tens of cavities? So what we made here is a single bus waveguide. It's a single mode photonic waveguide that evanescently couples, in this case, to 13 photonic crystal cavities. So when we do spectroscopy, when we measure the reflection spectrum of this photonic structure, we can access 13 photonic crystal cavity, and we can do experiments on many cavities in parallel. Okay, so this is what the devices look like. We have a tapered coupling region. We have photonic crystals. So the photonic crystals are these whole periodically patterned holes on the side. And then we have an end mirror that's at the end of the waveguide. Okay, so we put these structures inside the 4 Kelvin cryostat. The sample sits on the stage like this. We couple with lens fiber. We get about 30 to 60% coupling efficiency to these photonic devices using standard techniques. One of the kind of archaic methods that we use to tune cavities is by condensing some gas onto it. So whenever you fabricate a device, it doesn't come exactly at the frequency you want it to. So you'd like the way to tune this. You could brute force it. You can make 1 million devices, but it's nice to be able to tune them. So what we do is we puff some nitrogen gas, and that condenses a thin layer of nitrogen on top of the photonic structures and changes the refractive index just slightly. So that allows us to tune the cavities. So with gas condensation, you can think of this like some kind of atomic layer deposition method. You can tune the optical resonances. But this is a very archaic method that I really strongly dislike. What we'd like to be able to do is to be able to individually control these cavities, get them exactly where we want them to. Something a little more modern and faster. Okay, so I'll talk about the technique that we developed. So if you kind of remember this waveguide structure, we're launching laser light into this waveguide. And each of these lines that you see here correspond to an individual photonic crystal cavity. So if I park my laser on one of these cavities, what's going to happen is that I'm going to get resonant enhancement of the intensity on one of the photonic crystal cavities, right? So I can selectively determine where my laser intensity will be maximum. Okay, so if I start cranking up this laser intensity, what happens is that I can start locally heating up this resonance. And because this nitrogen has a sublimation point around 20, 30 Kelvin, I can selectively remove the nitrogen I deposited from just one of these cavities. So basically, this is a data showing that we can reconfigure these photonic crystal cavities. So what we're doing here is we first park on the first resonance, we tune that one using basically sweeping the frequency of the resonant laser, and then we move on to the other one, we can tune that, etc. But this allows us to realize regular grids and allows us to avoid disorder in these structures. So we've been studying how this coupled cavity arrays on a waveguide behave. There's some interesting effects because of the end mirror. There's some feedback. Your kappa E changes as a function of the reflection phase and so on, but I'm not going to talk about those details now. All right, so this is what the inhomogeneous distribution of T-centers on the waveguide itself looks like. But if we look at the spectrum inside a cavity, because the cavity has a much smaller mode volume, we can easily isolate single emitters. In these structures, we have per cell enhancement that modify the excited state lifetime from about a microsecond to 70 nanoseconds. So we get a pretty nice reduction of the lifetime. And the fact that we have many cavities allows us to get some statistics a little more easily. So in the same device, we've characterized 4 T centers that were in 3 different cavities. And in the specific experiment, we got a range of per cell enhancement factors. So what's nice about this is that we can access all these cavities through the same fiber and the device. Okay, so we're thinking about, okay, what's kind of, this helped us solve our yield problem. So we can have many, emitter cavity nodes in a single device, but we started thinking about, okay, is there something cool we can do with this? Well, the first thing we looked at was, we thought about, can we do some kind of multiplex operation of different cavities? So each of these emitters is at a slightly different wavelength. So I can maybe, tune the first cavity onto the first emitter, the second cavity onto the second emitter, and I can use frequency domain multiplexing to access both of these systems at the same time. And that's exactly the spectrum you're seeing here. So the red curve is the reflection spectrum. So that's the classical S11 reflection spectrum. And the green and blue are the fluorescence spectra. So we can, tune each of these cavities to be on resonant with the emitters that are inside those cavities. Okay, so for the experts, this is basically the first device that we made. Our Qs were very low. Now we get about Qs of 50 to 100K, and our emitters have a line width of about 1 to 2 gigahertz. So in terms of the cooperativity, we're in the 0.01 regime right now. Yeah.
Wait, how does that line width relate to the T1?
This is much, much broader. Yeah, so we're in the per cell regime. Oh, you mean the emitter line? Yeah. So that's where the cooperative limit comes from. So the gamma here is gigahertz scale. So the per cell enhanced lifetime is 70 nanoseconds. So 1 over 70 nanoseconds is like a few megahertz. So we're like 10 to minus 2 to 10 to minus 3 range. Yeah. So you compare, that's my 4G squared kappa is 1 over 70 nanoseconds, the per cell decay rate. And then the total line width is gigahertz. So we're in the C of, 1e minus 3 to 1e minus 2 range. Yeah.
T1s were, I thought those T1s were actually measurements.
These are T1, yeah. So we have, I guess the shortest one is 70 nanosecond lifetime. Sorry, it seems like I didn't answer your question.
Well, I'm just trying to how you're measuring 70 nanoseconds.
Yeah. Oh, it's dephasing. Yeah. We're actually looking at, right now, we're studying the noise spectrum of that dephasing. So we're studying our homogeneous line width. So we do saturation spectroscopy, which gives us the instantaneous line width. That's about 200 megahertz. So at short time scale, our cooperativity is actually like closer to 1e minus 1 to 1e minus 2. And there's a lot of, that's where the real research is. So the research is about reducing that line width. I'll touch upon that later. One of the cool things is in silicon, we can apply a kind of more active feedback or charge noise engineering methods by applying bias fields or embedding them in PN junctions and so on. But those are the kinds of things, engineering tools we want to use. Yeah. As a kind of a simple principle demonstration, what we did here was to use a single laser. It's a cool laser where you can hop the wavelength by nanometer scale at a couple of microseconds time scale. So what we did was we used one laser it was basically hopping between two different wavelengths, switching between two different wavelengths at microsecond timescale. So basically, we ran single photon generation experiment between two emitters in two different cavities, and we get pretty good G2s and so on. So this is basically doing single emitter experiments. Okay, there's some multiplexing in there, but in circuit QED, in superconducting circuits, these bus-mediated interactions are actually a very nice engineering tool. So you can engineer methods of realizing long-range interactions. So you could think about using this bus as a mediator to couple cavities that are far apart from each other. So one of the things we started doing is like, can we start doing the circuit QED-like things in the optical domain now? So this is an experiment where we're tuning the lasers. We're tuning the two cavities. So what you see here is some avoided crossing-like response. So one of the cavities is crossing through the other. These are not direct coupled cavities, so it's not really a simple avoided crossing. You need to do the full scattering matrix, but qualitatively, it behaves like coherently interacting cavities. So we did this experiment where the T-center was in one of these cavities, and then we brought in the second cavity such that the photonic mode is now delocalized. Okay, so when you bring the two cavities on resonance, you expect to form, symmetric and anti-symmetric super modes, right? So if you if you want to probe this, if you want to show that this is happening, how can we use the emitter to verify that? Well, the Purcell factor depends on the Q over V, right? So if your effective mode volume is doubling, then your Q over V is going to be reduced by a factor of 2. So what we did was basically use the qubit as a probe to measure this mode hybridization across two cavities on the waveguide. So we did the T1 measurement. Maybe focus on the blue curve. The oranges we're still trying to understand. I think there's noise in there. If you look at this blue curve, what you see is that the first cavity is normally on resonance, but once we bring the second cavity on resonance with the first one, the lifetime doubles. And that's basically because of this mode hybridization between the two cavities. Okay, so on the photonic side, we're making some progress. This is a very new system, but we're already at the 1e-2 to 1e-3 cooperativity range. I think we can boost the cooperativity by maybe 1 or 2 orders of magnitude just by the photonics. I mean, we really haven't worked much on that front. But secondly, really, to make this system higher performance, we need to fix the line widths. So on that front, I'm actually quite optimistic that this line width broadening comes from spectral diffusion, and it's ultimately from charge noise. So there's charges kind of hopping between different trap sites in the material. But people have shown this in 3-5 quantum dots, also in silicon carbide PIN junctions. If you apply some bias field, you can sweep out this excess charges. Okay, so that's one of the things we're really excited about working on now, to bring this gigahertz line with 10 megahertz. Then we could maybe do high cooperativity optical cavity QED and silicon photonics. Yeah.
You want a couple of tubes, do you have to get them on resonance?
Yeah. So
would you do a photonic conversion?
That's another option. So one of the the cute things about this platform that I like, they're already in the same spatial mode, right? They're just in different frequency modes. So if you take this through a phase modulator, you can do frequency domain, HOM, and instead of beam splitter, Hongao-Mandel, you can mix the modes. Kind of like tricks you're using with your asymmetric squids, etc. Right? You could also think about closed system versions of this, like with a nonlinear oscillator. Nonlinear photonic oscillator, you can make this in silicon. Now that we're in silicon photonics, I think it's not that crazy to kind of bring these more active electro-optic components or MEMS, based tuning, etc. So from being able to engineer the devices, I think we can make tens of these and add more tuning knobs in there. But we will need tuning.
Do you expect the gating to between the T-center?
Yes. Yes, but that's a limited range. Okay, I'll take the aside because I think it's kind of interesting. So in deep color centers like SIVs or silicon carbide, the electrons are really close to the middle of the band gap, and they're it's very strongly bound to the defects. Okay, so in the system that we're looking at, when the optical excited state of this defect is a state where the core of this defect is negatively charged, so it has some fixed shells. So the core of this T center is a negatively charged core, and then there's a hole that's weakly bound to it. So this is basically like a hydrogenic system, very much like excitons, except the binding energy is something like 30 MeV. Okay, so actually, if you look at this excited state structure, it's like really very similar to acceptor levels in silicon. So actually, there are Rydberg series associated with higher excitations of this hole that's weakly bound. So you can observe these Rydberg series and so on. The reason I'm making this side is that because this hole is weakly bound, it's only by 30 MeV. If you calculate like the tunneling rate, so if you apply some electric field, you tilt the potential, the atomic potential, and you start getting tunneling, ionization, just like in Rydbergs. And this ionization the field is relatively low. So this is just based on calculations, and I think we'll be able to maybe 5-10 gigahertz, but after that I think it will ionize. Which
So regarding charging modes.
Yeah.
So do you have idea of the time scale of charging modes?
Yeah, so we're measuring homogeneous line movement right now. So we're doing basically saturation spectroscopy. Their preliminary results show that at the lifetime time scale, it's close to 200 megahertz. We're actually now doing this time dependent study, so hopefully we'll learn that. I think the main question is it laser activated or is it? It's. I mean, we're at cryogenics, so it's probably laser activated. I don't think there's an intrinsic time scale to it. Yeah. Okay, how much we have time? Okay. All right, this is good. It's a new system, so I think please ask all your questions. We're also figuring out a lot of the stuff along the way. All right. Okay, so we have a lot of AMO physicists in the room as well. So when you have optical transitions, you can use them to polarize your spin qubits. And when I told you that the ground state of this defect is a electron spin 1/2. It's really its G factor is isotropic. It's like really G equals 2. It's really like an electron in vacuum, more or less. But the excited state is this whole spin, which is loosely bound to the defect. And that has some complicated spin orbit interaction that comes from the value states of silicon and so on. So the excited state has a different G factor. Okay, so when we apply a magnetic field, we get some differential Zeeman splitting between the ground states and the excited states. So that allows us to resolve different spin-dependent transitions, these what are labeled A, B, C, and D. So we can use these to do optical spin initialization and readout. So in order to do spin control, in addition to our photonics platform, we also added some microwave circuits. So it's a superconducting niobium transmission line, such that we can effectively deliver microwave pulses to our spins. And we've done 2 laser spectroscopy. We can observe all these 4 transitions. We can identify the G factors, the Zeeman splittings in the ground state and the excited state. And when we pump on one of these transitions alone, it goes dark. We pump to a dark state. So if you're doing just optical experiments, you need to repump just like you do in atomic physics and so on. And this is kind of some example data showing this time scale. We can optically polarize these spins by pumping and use the same mechanism to read out. Just by this incoherent mechanism, we can already characterize T1. So we measured it up to 100 millisecond. So the spin polarization is longer than 100 millisecond. Beyond that, we just stopped measuring. So the T1 time is very good, and that's what we expect based on the electronic structure. Of course, we care more about the coherence. So this is some preliminary data. We're now doing coherent control of this electron spin, and the spin coherence time is more or less what you would expect. So the echo coherence is about 250 microseconds. We started doing some CPMG, it keeps going up. So the results seem consistent with, spin qubit results in silicon. And now we're working on 28 silicon epitaxy to make these coherences even better. So the spin part of the story is already quite good. I mean, we didn't have to do anything really to get to this millisecond coherence. So the real science and whether, for the quantum community, this platform will actually enable new things, it will be determined by the optical coherence properties. And there, the name of the game, as usual, when it comes to solid state devices, understanding noise and mitigating that noise. So that's what we're going to be focusing on. Hopefully in a few years, we'll be doing high cooperativity optical cavity QD and silicon photonics. Yeah.
What is the spin initialization fidelity? Why is it?
It's good. I think it comes from the resolution of these Lorentzians. Yeah, I don't think we've characterized that. If I eyeball, maybe like 90% or something. Yeah. So if we apply a larger magnitude, I mean, it's like how selectively you're driving one of these transitions versus the other one. T1 is really long, right? So you're not competing against that. It's really like detuned scattering that limits you. So yeah, larger B field help, but there's also these cross transitions, D and A, which are kind of far separated. Yeah, so I think that will be okay. Yeah, but we have to, of course, study, indeed verify. Okay, so I'm roughly at the halfway mark, right? Yeah. Okay. So these were the good defects. Okay. By the way, I also don't want to give the impression that this T center is the ultimate thing in silicon and that all problems are solved. I actually would very much like to have a better emitter, and I'm convinced that there are more because if you just think about the combinatorics of these different defects, we are also collaborating with ab initio theorists like DFT folks who are predicting many variations on this. Another challenge of this T center is that it has 3 impurities. That's kind of like a hard molecule to form. Like all stars need to be aligned. I think what would be really ideal is like either a single impurity or like maybe 2 at most. Ideally, those are kind of easier to make and more deterministic. Okay, so this optical part was a story where we're using defects to bring single photon level optical nonlinearities to silicon photonics. So in the second part, I'll kind of switch gears and talk about superconducting circuits. And in this case, the defects will be a loss mechanism, the coherence mechanism for superconducting circuits. Okay. So we have, I guess, there's a lot of superconducting work here. A lot of you are also probably familiar with this. People show this plot in different contexts. I've seen this plot being shown as an example where people say, okay, we've been having amazing progress and it's keeping on going on. But when I present it, I usually see something else. I usually see that, this was, the qubit coherences were getting better, but then flatten out is how I at least personally interpret this. I think we've been kind of stuck at the 100 microsecond to millisecond range for some time.
You're missing a decade also.
Yeah, exactly. I mean, there's a hidden decade there where, and then if you look at the y-axis, that's, this is 10 to the 3 microseconds. So, yeah, and that's, optimistic that's still where we are. Yeah.
Arguably, we're up to 30 milliseconds or so.
But you're counting like low frequency?
No, like the superconducting cavities. Like the high numbers are the 3D cavities.
Yeah, there's other forms of cheating here. Yes, the high numbers are cavities. They're not really. Okay, they're weakly nonlinear systems and so on. Anyways, my message, my version of this plot is that we've been a little bit stuck, and I think we need to revisit some of the fundamental mechanisms that put limits, because we're in a bit of a situation where there's a death by 1,000 cuts. There are just so many effects that are ongoing. and we really need to understand as many of them as possible. The way I'm going to phrase one of the loss mechanism, I'm going to talk about a loss mechanism and our specific interpretation of it. So when you make a superconducting circuit, you have electric fields everywhere. You're making nonlinear LC oscillators. And if you have any kind of piezoelectric response in this circuit, what it's going to do is it's going to create forces on the lattice, and it's going to transduce energy from the electromagnetic domain to phonons, right? So piezoelectric response will convert the electromagnetic energy you have into phonons. So when we talk about piezoelectric response, I'm kind of meaning this in a very general sense. So I'm kind of here interested in any mechanism that takes electromagnetic energy and turns it into phonons. And there's many ways that this can happen due to defects and interfaces in materials. So fundamentally, what's the origin of this? The origin of this comes from symmetry breaking in materials. So if you had, infinitely large material with a perfect central symmetry, you have a perfect crystal. You don't have any kind of piezoelectric response, but you can break symmetry in different ways. Your lattice may not have central symmetry, so you can have bulk piezoelectric materials like quartz, lithium niobate, aluminum nitride, and so on. So these kinds of systems are not what I'm going to talk about because these are things that we understand. Okay, so we basically don't make qubits on lithium niobate. We don't make qubits on aluminum nitride, and so on. So these are not really qubit substrates for that reason. So we normally work with central symmetric crystals like silicon or sapphire, and the bulk of the material does not have any piezoelectricity. But as soon as you start dealing with some kind of real device, the symmetry is broken, and this can come in different forms. Having a defect breaks symmetry. Having heterostructures, having interfaces breaks symmetry because, what is central symmetry? It's like you invert your coordinates, you need to get the same thing out, right? But if you have, substrate, air interface, obviously that inversion symmetry is broken. So as soon as you have defects, interfaces, or heterostructures, your symmetry is broken. So kind of fundamentally, you might have this piezoelectric transduction effect. So one of the forms of symmetry breaking that's very common and gives rise to this loss mechanism is these material defects called two-level systems. So this is a topic that's been studied in low-temperature physics for many decades. So if you have an amorphous material, there are different forms where you can have low-energy excitations in these glassy systems. And the honest answer is people don't know exactly what they are. It could be something like tunneling atoms. There could be some bistable configuration of a bond. And these two bistable configurations can constitute a two-level system. It could be some rotors, it could be some dangling bonds in electronic states and so on. But what's common is that people use this standard tunneling model to describe these systems phenomenologically. So you can effectively describe them by a double well potential with some asymmetry energy, where the asymmetry depends on the amount of strain you have as well as the electric field you have. Okay, so for these systems have some static electric dipole moments of order dBi, so similar to atomic systems. What's kind of maybe an unusual thing for most folks is that they also respond to strain. So just like electric field gives rise to energy shift, like Stark shift, in solid state materials, instead of electric fields, you can apply strain fields. You can compress the material. That also gives rise to something similar to a Stark shift. So that's what we call deformation potential, okay? So if you apply unit strain to these defects, they shift in energy by 200 terahertz, okay? So how does this all relate to phonons? So, well, they have an electric dipole moment. So they behave like absorbers, okay? So in laser physics, you might have heard about saturable absorbers, right? You might have a resonant media and you can saturate it. And if it's a bunch of two-level systems, it behaves like a saturable absorbing media. So these two-level systems essentially behave like a saturable absorbing media. And ultimately, they dissipate the energy, not by emitting photons, but by emitting phonons. So in essence, you can think of this as these defects as microscopic transducers that take in some electric field and then convert it into a lattice vibration to a phonon. Okay, and this whole mechanism constitutes a loss mechanism for superconducting qubits. So there's a lot of work in the field trying to get rid of this stuff. Okay, so these two-level systems reside in amorphous materials. And if I take a cross-section of a typical superconducting device, I have metal, I have substrate. So the bulk of these materials are usually good. But what's problematic is interfaces. So what happens between the silicon and aluminum, you usually have some amorphous layer, or you can also have some amorphous layer, surface oxides on your aluminum, on your niobium, and so on. So people are working very hard to get rid of these. And there's a lot of work by modifying the geometry to understand and minimize the losses at surfaces. So one kind of jargon I'm going to use is this phrase called surface participation. So surface participation tells you the following. Imagine you have some electromagnetic mode, right? You have some total energy associated with that mode. Surface participation tells you what percentage of that energy is in the top few nanometers of your surface, okay? It's basically how much of your energy is, electromagnetic energy is localized to surfaces. When you have loss, it usually scales. If it's due to these surface effects, it scales by the surface participation of your electromagnetic mode. If you make big cavities, this number is small, so your loss is small. Okay, so only a small fraction of energy, electromagnetic energy of order part per thousand, lives at these interfaces, but it still dominates the loss in most circumstances. But in the past few years, there's been a lot of advances in improving these amorphous interfaces. And now some of the experiments are reaching a regime where we are not limited by losses due to these amorphous layers, but we're limited by losses in the bulk of the substrate. Okay. So we're reaching a regime where defect-induced loss from the substrate is starting to limit the quality factors of qubits. Okay, so the nature of these defects and absorbers in the crystalline substrates is going to be very different from amorphous materials. In amorphous materials, we just don't have a good handle. We don't know what they are. But in defects in crystalline materials is the first part of my talk, right? We can write down Hamiltonians, we can understand them, and so on. So we started thinking what kinds of defects would give rise to a two-level system response in silicon. So the two things we often consider is, your donor and acceptor concentration in the material. So we first looked at donors. So if you think about phosphorus and its level structure, I'll cut the story short. It doesn't have a level structure that resembles a two-level system. Okay, so it's a singlet orbital. So there are no two electronic states that behave like a two-level system. But when we looked at boron, it turns out that its level structure has a ground state where you have two degenerate orbitals. Okay, so the ground state of this defect has two different electronic orbitals that are nominally degenerate. And when you fabricate a device, when you deposit some films, you introduce some stress in the material. So what this stress does is break the symmetry and start splitting these levels. Okay, so in your material, if you have strain inhomogeneity, that gives rise to different splittings for these acceptors. Okay, so in the end, at the end of the day, what you get is these acceptors show up as some systems with two orbital states that look very much like a two-level system. And if you compare the typical parameters, they have an electric dipole moment of about dBi, and also strain sensitivity that's also similar to the amorphous two-level systems. So based on this kind of just thinking about these defects, we predicted that acceptors in silicon should be a TLS for superconducting circuits. So the prediction is boron is bad, phosphorus is okay. So to test these, we made some resonators. And what we find is that in undoped silicon, our losses are dominated by surface losses, the amorphous. But if we dope the silicon, our losses are dominated by bulk. And the losses we get from bulk, they're not just some resistive loss. It actually follows the saturation, the saturable absorber response that you expect from a two-level system. So as we increase the microwave power, the Q improves because they saturate and they can't absorb any more power. So basically, these borons in silicon are showing all signatures of a two-level system. Their temperature dependence also shows the saturation response you would expect. And then we repeated these experiments for different concentrations of boron in different wafers. So we basically purchased several float zone wafers with different boron concentrations. And here I'm plotting the internal quality factor of resonators as a function of the boron concentration. And we see a very clear correlation. So we think that with all this evidence, we can conclude both from the theory and experimental evidence that borons are acting as a TLS pad for superconducting circuits. Okay, so this is kind of nice basic science, but this is something that's relevant. So if you've ever bought a silicon wafer, the thing you look for is resistivity to give you a proxy for how pure it is. So oftentimes you can buy wafers at a few 10,000 ohm per centimeter, ohm centimeter. And what this tells us is that if our extrapolation is correct, this actually puts a limit on the Qs you can get at the 10 to the 7 level. So there's some error bars here, but this is a serious limitation for the maximum Qs that you can achieve, maximum loss energy. We're now thinking about ways to get around that. In particular, we're thinking about whether compensation doping or straining the material could help us engineer either the charge state or the splittings of these defects. Okay, so and then just to provide some perspective, I'm particularly excited about this work because this TLS and what they are has been an open question in the field for decades. And to my knowledge, this is the first time where we can point and say, your TLS, here's a TLS, this is a boron in the material, here's this Hamiltonian. We actually did some magnetic field dependence as well. We actually have some predictive power in terms of how these TLSs respond to magnetic fields as well. So there's at least now one TLS whose microscopic origins that we understand. And moving forward, what I'd like to kind of claim is that we can understand TLSs in bulk. So that's what we do all the time for color sensor research. So we understand the Hamiltonian's electronic structure of defects in crystalline materials. So these results I think will be similar in sapphire. So there'll be probably similar defects with similar properties. How many minutes do I have? 3, 2. Okay. All right. So in the last part, I'm gonna very quickly talk about this fun effect that we observed that we're calling interface piezoelectricity. So the second mechanism I introduced that makes piezoelectric response is interfaces. So imagine that you put aluminum on silicon. If you've taken a solid state device physics class, one thing you learn is you start drawing these energy band diagrams, right? And think about Fermi levels, how the Fermi levels and electron affinities kind of align. If you have a metal semiconductor junction, the Fermi levels are usually not aligned. So what you have is charge transfer between the two materials. So when you have charge transfer, you have a fixed electric dipole moment at that interface, right? And if I have these charges that are fixed at the interface and I apply some strain, what I'm going to do is I'm going to create some extra potential, right? Or if you think the other way around, if I apply some electric field, I'm going to apply extra forces on these charges. So what we realize is that these charges can give rise to electromechanical transduction, some piezoelectric response. Okay, so in order to test this, we made a surface acoustic wave transducer. So we made IDTs of aluminum directly on silicon. So normally you would say this is a terrible idea. This should not work. And we thought it would not work actually. Yeah, so we made IDTs, we made the launcher, surface acoustic wave launcher and receiver. And then we measured the S21. In the frequency domain, you get these kind of interference fringes, but if you look in the time domain, it's more clear. You get an impulse response due to phonon transmission at a slow propagation velocity. And this corresponds to detecting a surface acoustic wave. And to make sure we're not being stupid, we kind of change this distance between the electrodes, and we see this surface acoustic wave transduction delay scales with the distance, and we can indeed measure the speed of sound or speed of surface waves on silicon that's consistent with literature values. So it's pretty clear that we're measuring this effect. So this is an effect. So you can put metal on silicon and get piezoelectric transduction. All right. So is this something I should worry about? Is it something I should use? As a way to calibrate, what we did was to compare the transduction efficiency with some aluminum nitride thin film. So we compared the S21s. This is not a perfect calibration, but it gives us some sense of the strength. So if we do a calibration using a reference film, we think that the effect corresponds to having about 8 nanometers of aluminum nitride at the interface. So we repeated this with multiple surface preparations. It's a pretty robust effect. Shows up in p-type, shows up in intrinsic, shows with oxides at surfaces, and so on. We see the signal all the time. So now we're trying to kind of more carefully calibrate it and put a number on like how much of a loss mechanism this would constitute for qubits. So the numbers are currently from like 10 hertz to kilohertz range, depending on the mode matching you have between the two systems. Okay, with that, I think I'll end here. So hopefully I gave you a flavor of what we do and convince you that defects can be good and bad. We should study them nevertheless. And I want to thank the whole team who's kind of really doing this research, and thank you for your attention.
So traditionally, first questions go to students of both sides.
So I have a question on the list. If I understood correctly, if there's a strain distribution in your substrate, that should correspond to like a PLF frequency distribution.
Yes.
Check outside that frequency distribution.
So yeah, based on, we did console simulations. Let's say we deposit some metal, we get 100 megapascal level at the surface, and then gradually falls off. So if we take that distribution, let's say 0 to 100 megapascal, that's kind of the strain inhomogeneity. If we map that to frequency inhomogeneity, that corresponds to 0 to 100 gigahertz. So we're just probing between 4 to 6, and in that range, we think it's flat. I think if we looked at higher and higher, we would maybe see the fall off. But one of the things we really want to do is make a MEMS structure. So maybe make a capacitor on a doped silicon with wafer, and then just stress this thing, and then it should start low Q, and then once we start splitting this to above 5 gigahertz for all of them, then the Q should improve. So yeah, those are the kinds of microscopic studies we're planning to do. Yeah.
I have a question about the charge noise or noise checking.
Yeah.
You also see kind of discrete jumps, I guess, of your qubit in terms of frequency. Like say that these minute time scale. And
so that we on the optical lines we don't see that.
that's mainly just broad.
Yeah, we have not seen. I mean, we've done many spectra. I know this is common. Like we used to see it a lot in diamond, and yeah, here we don't see any ionization like optic laser ionization. So it's just works in that sense. And yeah, it always seems to be like Lorentzian-like broadening. We know that there's a thermal component to this line width. So we're at 4K. There's like 200, 300 megahertz thermal broadening. We might need to go a little bit lower in temperature to 3 Kelvin or so. Yeah. We see something weird in our electron spin resonance. We see a doublet, and that doublet is stronger than the calculated hyperfine interaction. So either the calculation is wrong, or there's some kind of mechanism that changes electron gene factor into discrete values. So there's some open questions we haven't discussed. We're still trying to understand. The boss. Yeah.
Yeah. Connecting to the center, do you know how much like non-radiative like decay is part of this? Because they seem always pretty like different. So I'm just wondering.
I think radiative efficiency is actually pretty good. Like we tried to calibrate that. I don't remember the exact bound, but we said like if we track all the kappa E's and coupling efficiencies, kappa I's, I think we said it's more than 50%. Yeah, it's okay.
Yeah, I guess like just because even if, even in a symmetric crystal, right, like if it has a dielectric constant, you get like kind of a second order induced piezoelectricity. And I guess it should have a different dependence because it's
yeah. So you're talking about the electrorestrictive effect.
Yeah,
like that's
basically,
like yeah.
And so I guess if you wanted to look, like with your same setup, you could probably look at it by, I guess you could, if you put a bias voltage on it.
We did that.
And then
yeah.
I guess it'll, if in some sense it saturates at the difference in the work functions, then that would be a good.
Yeah.
That's basically
so we've done this bias measurement, and so whether you're forward biasing or reverse biasing changes the amount of charge you have. So we do see a change in the transduction efficiency under reverse versus forward bias. So that's one evidence that it's not that, but also we did power dependence. It's like as linear as it gets. So it's a linear effect. It's not like some E squared plus strain, like it's not a three-way mixing effect.
Yeah.
So it's we did a very wide dynamic range. It's a linear response. So one way I think about this is that you can reconcile this interpretation with what you're saying. The built-in potential
exactly.
is your bias.
Yeah, of course.
Yeah.
Okay, in that case, the run applause. Thanks.
No, I mean that was good. Yeah.